this. Now, testing. Okay, need to do a little bit of testing here. Let me check to make sure. Oh, there's a lot. What is this? Filter, output gain, turn the gain down. Okay. Gain is down. We're at 50% volume. Let me see if I can hear myself clearly. Not really. Let me make it a little bit louder. Alright, bit louder gain here. Try 2. Dude, what is this graininess? Oh no. Try this setting. Alright, this actually feels a lot better. Alright, how's it going, Ed? How's it going, Josh? How's it going, John? We got... Let me turn off this. We got a new little buddy here. Let me see if I can get him working. Yeah, that's much less bad. I agree. Okay. Let's try. There we go. Exciting insider information. I don't have any insider information, unfortunately, Leo. All I have is this little robot. Let's see. He's looking at us for sure. Let's move him a little forward. Okay. Yeah, that is a little humanoid robot that I got recently. The story of receiving this little humanoid robot is quite crazy. I had to buy it with Bitcoin, and they shipped it from China, so this might be literally the last humanoid that gets out of China before the AI restrictions come in. So I'm going to be developing on it. I literally just got it just a couple days ago, so I didn't have the chance to put that GPT-4 Vision demo running on it, but that's what I'm going to be working on, is get that GPT-4 Vision in there so that we can basically get it to just autonomously walk around and do things. You know, here's you can move it forward. It's all written in robot operating system, so all open source. Yeah, this is another mascot. All right. But let's actually get to the video, because I think we already started. Yeah, this already started 2 minutes ago. Let me check, make sure the X is going. It is live. All right. Let's announce it. We're going to be blowing the shofar horn today, so a little break from the didgeridoo. This one's kind of hard to blow. Give me 1 second. All right, there you go. That's about the best I can do. It's a really high-pitched horn. It's quite unpleasant, unlike the didgeridoo, which is quite pleasant to hear. All right. So today, and welcome to another Hoopo stream, we're going to be looking at Emu Video and Emu Edit. So Emu Video and Edit are two papers that came out from Meta, so the Gen AI group at Meta, the generative AI group, that is, of course. And there's actually a previous Emu paper somewhere here. I have it pulled up, but yeah, this one here. So this is the original Emu paper, Enhancing Image Generation Using Photogenic Needles in a Haystack, also from Gen AI group at Meta. And emu, I guess if people don't know, is like a type of flightless bird, kind of like an ostrich. So they're kind of like riffing on llama, right? So I guess here's literally a picture of an emu, but llama is their language model, and then emu is their kind of image video type model, 2D images, right? So not 3D stuff, just 2D. But yeah, pretty cool little paper that we're going to get into. We're going to get into those three papers, but also one little detail here that I thought was pretty cool is that none of these are journal papers. So if you notice this, these papers are just papers that they just put on their website. So these aren't papers, these aren't preprints, these aren't papers that are going to end up in some conference or some journal. They're open source entirely. You know, they just literally put them on their website and they're like, here's the paper, read it if you want. We're not going to pay to put this in some journal. We're not going to be beholden to some weird journal that tells us that we can't publish this or we have to do this or blah, blah, blah. So I don't know. I like the open source, and I like the going around the publishing monopoly cartel cabal that is machine learning conferences and journals. So pretty awesome work. So we're going to start with Emu Video, but first, before that, we're going to maybe look at some of the results for this. So this is Ishan Mishra. Ishan is the most senior person here. This is this guy. And he released this, which is basically just a bunch of cherry-picked examples of this video, and it's actually quite good, right? You see that? It's the way that it can separate out the foreground and the background, the interaction of the water. You know, there isn't like all this weird morphing that you see. So quite impressive. Of course, these are cherry-picked, so it's going to be, you know, it's not always going to be like that. But if you're going to compare cherry-picked examples, you compare it to other cherry-picked examples. So these are cherry-picked examples for Runway ML, which is a startup. They have a video generation called Gen 2, and this is theirs. So also pretty cleanish, you know, like it's relatively, I would say that maybe one negative of this one is that they're a little bit more still. So if you notice the Gen AI ones seem to have a little bit more motion, you know, it's not just kind of like a very passive kind of outwards panning or just like very subtle effects like the water or the waterfall. But I wouldn't say it's necessarily outrageously different. You know, I would say these are both a little bit comparable. You see a little bit of kind of morphing going on there where the colors kind of morph, the shapes kind of morph on this parrot. So this is a third competitor. So this is Pika Labs. Pika Labs is another startup, and this is, I don't know who this is, some rando who just basically created a Pika Labs text-to-video, but I think it's indicative of kind of the quality. This one is a little bit worse. You can see that there's a lot of kind of weird morphing going on with the hands, and the people in the background kind of change, and like it's a little bit more weird looking. Granted, this is a more difficult thing to do text to video for, a bunch of people dancing at a gas station compared to just like a static shot of like grass moving in the wind, but it does kind of seem, just from my complete cherry pick analysis here, that Pika Labs is a little bit worse, and then Runway Gen 2 is about, I don't know, about on par with the Emu Video. But Runway Gen 2 and Pika Labs, those things are not open source at all, right? These are secret sauce developed in a startup, and they're never going to release it because their entire business model depends on them not releasing it. So getting basically state-of-the-art video generation Open source is pretty great, so you got to commend that from Meta. Yeah. Okay. So let's get started here with Emu Video. We present Emu Video. We're going to read the abstract first. A text-to-video generation, right? So text-to-video, you give it some piece of text, and then it'll generate the video for you. Factorizes the generation into two steps. First, generating an image conditioned on the text, and then generating a video conditioned on a text. And this kind of like two-stage pipeline, I feel like pretty much every single text-to-video model does this. The other papers that we've read on this channel about text-to-video do the same exact kind of thing, right? It's basically taking a diffusion model, generating an image, and then figuring out how to basically extend that image over a variety of frames. The generated image, we identify critical design decisions, so a couple little tricks that they've figured out in order to make this work out. So one trick here, adjust the noise schedules for diffusion. And what do they mean by that? So I have a bunch of diffusion pictures pulled up. You know, you guys know that I love my diagram. So here we have a diffusion model, right, going from pure noise over here all the way to the image of the dog. So a diffusion model is removing noise, right? So you can see how it's slowly removing noise. And there is basically a function that adds a different amount of noise depending on the step, right? So you can see how maybe here you would remove or add more noise, and then here you would remove or add less noise. So the amount of noise that you add that is dependent on the actual time step, so where you are along this continuum, is called a noise schedule. So they did a little bit of trickery with the noise schedules, and then also multi-stage training. So we'll see what that exactly means. Enables us to directly generate high quality and high resolution videos without requiring a deep cascade of models as in prior work. So a deep cascade of models as in prior works, kind of just saying that it's a relatively simple kind of pipeline. Yes, it is a multi-stage pipeline. You have the image generation, then you have the video generation, but other works that we've seen for this can get very complicated very quickly. They have like different hierarchies, different resolutions, like different cascades that feed into each other, and it starts to get a little complicated. So the fact that they try to get to state of the art, and they basically did by pulling away some of the complexity, I think is a breath of fresh air, right? Because a lot of times these computer vision pipelines, in order to improve the quality, they generally tend to get more complicated, and then it gets more difficult to reproduce, more difficult to create, more difficult to understand. So the fact that they were able to get state of the art by kind of pulling away some of the complexity, I think is a general win for humanity here. Our generated videos are strongly preferred in quality compared to all prior work, 81% versus Google's ImageN Video, 90% versus NVIDIA's Pyoko, and 96% versus Meta's Make a Video. Our model outperforms commercial solutions such as Runway ML's Gen 2 and Pika Labs. And finally, our factorization approach naturally leads itself to animating images based on a user's text prompt, where our generations are preferred 96% of our prior work. So kind of this goes to the point that the Yivian was it the Yivian? We need more benchmarks. Yeah, so we don't really have benchmarks for video generation, right? It's kind of getting to the point where quantitative benchmarks, where you can just put in two things and get a number for both of them and then compare numbers directly, that doesn't really work anymore, especially for things like text to image or text to video. So the way that these evaluations or benchmarks are basically done now is these user studies. So they basically have people sit in a room, and the people are basically get to watch this video, and then they get to watch this video, and then they get to watch this video, and they just have to pick which video they like best. And they don't actually know which video is which, right? So it's kind of like this double blind situation. Maybe not double blind, single blind study, I guess. And that's kind of what they mean here by human evaluations. It's basically you have humans sitting here looking at these and saying, I prefer the video on the left, or I prefer the video on the right. And if you do those, which I think are actually a pretty good way of determining the quality of text to image and text to video, you basically get the state of the art, which is this. So not the traditional way to claim state of the art, but I think it's an acceptable way to claim state of the art. Mirasol 3B. What is that? Okay. So Abstract is important, but introduction generally not super important. Only really the end of the introduction is important, which we're going to read here. This is the contribution section. Sometimes it's also a list of bulleted points. So let's go into that. We show that text-to-video generation quality can be greatly improved by factorizing the generation into first generating an image and using the generated image and the text to generate a video. So first generating the image and then using the generated image and text to generate a video. Our multi-stage training enables us to directly generate videos at a high resolution of 512 pixels. So multi-stage training just means that it's not just one training phase, right? Right now, most people are familiar with pre-training and fine-tuning, but there's no limit to that. You could have like 10 different training phases if you really want. So multi-stage means there's more than just one. 512 pixels, relatively high resolution, I guess. We design a robust human evaluation scheme, JUICE, where we ask evaluators to justify their choices when making the selection in pairwise comparison. Okay, that's kind of cool. I haven't really seen that before, right? Innovation in the human evaluation itself. Emu Video significantly surpasses all prior works. Beyond text-to-video, so T2V is just text-to-video, Emu Video can be used out of the box for image-to-video, where the model generates a video based on a user-supplied image. Okay, so that's kind of clever, right? Where if they would have just done text-to-video directly without going into this intermediate image generation, then you would have only been able to use this in a T2V workflow, but because they make it multi-stage where you can basically first generate the image and then from the image generate the video, means you can, given an image, generate a video, which is a pretty cool workflow. Let me scroll up. I'm realizing that my head is kind of covering this. Let me also do this, like that. Maybe get a little bit more this way. Okay. Related work section, generally also not necessarily super worth reading, but maybe we scroll through it a little bit here. Quality text faithfulness. So Emu Video win rate percentage. So win rate percentage here, right? In the human evaluations, whenever a human picks one over the other, that's called a win. So the win rate is basically just every time that humans are shown Emu and then some other video, like how often do they pick the other one rather than the Emu. So you see here, Emu versus make a video, Emu versus image gen, Emu versus align your latents. These are all basically the other things to compare to. And quality text faithfulness. So text faithfulness, I guess, is like how, why don't we just read the description here. Since most models are not accessible, we use the videos released by each method and their associated text prompt. The release videos are likely the best generations, right? So they're saying that they're cherry-picked, and we compare without any cherry-picking of our own generations. Somehow, I don't feel like that's the case. They probably also cherry-picked. Emu videos significantly outperform all prior work. Okay, so you see here they're kind of slowly preferring anything over 50% means that Emu won. So as you can see, every single one of these bars is over 50%, which means that, for example, Emu Video versus Pika Labs, 96% of the time they said the Emu Video was more faithful to the text, and 98% of the time they said that the Emu Video was more higher quality. So the fact that all of these are above 50% is basically the proof of state of the art. There you go. There's your figure 2, which proves their state of the art. Okay, so here in the related work section, they're kind of just talking about different types of text to video, video generation, right? People used to perform with this with GANs, things like LSTMs, VAEs, whatever, whole bunch of historical crap that nobody really necessarily cares about. So let's go to 3. Section 3, the approach. This is where they're actually going to explain what the fuck they're doing, and that's what we're going to read. The goal of text to video is to construct a model F. So let's start pulling out our green highlighter, which is our terminology, model F. So you have some model F, aka a function that takes some input and produces some output. Takes as input a text prompt P, so P is the text prompt, right? Some sequence of little text tokens there to generate a video V. So a video V is basically a sequence of T RGB frames, RGB red, green, and blue. It's basically saying that images or frames are basically 3-channel images where each of those channels is red, green, and blue, and the red, green, and blue comes from the fact that our visual system has 3 different types of color cones in your eyes, so basically 1 channel per type of color cone. If we were mantis shrimp, and mantis shrimp have something like 16 different color cones, then we would be using 16-channel images, but because we're humans, we have 3-channel images. So recent methods directly generate the T video frames. Our approach builds on the hypothesis that stronger conditioning by way of both text and image can improve video generation. Okay. Preliminaries, a conditional diffusion model. So a conditional diffusion model is a generative model that is trained to generate the output using a conditional input C. Okay, so you have something that is conditioning the generation. And what exactly does that mean? Let's go here. So here we have a diagram of, I think, Stable Diffusion XL. I don't know, one of the Stable Diffusion models, but a couple different things here, right? So you see that first thing is that Stable Diffusion is a latent diffusion model, which means that you're performing the removing and adding of noise in the latent space. So here X is going to be your actual image. You're going to feed it through this E, which is an encoder. The encoder is going to convert your image into basically this encoded image, which is like a little representation of the image. You can't really know what it means as a human. To you, it just looks like a bunch of numbers. But to the encoder and to the decoder, it's a way of communicating that image in a more compressed format, right? So it's basically a compressed representation of that image. So that's what the encoder and the decoder are, this E and D, right? And here in latent space, so latent is the space in which those little latent images exist. That's where the actual diffusion process happens, and the actual diffusion model, because there's a couple different models here, right? You have your encoder, your decoder, but the diffusion model, this one, is this UNet. So this UNet takes in the latent and then basically outputs, here's the noise, right? So, and then whenever you run it to actually generate an image, you're basically removing the noise. So the UNet is telling you, here's what I think the noise is, or basically here is the image without the noise. And then you slowly do that for a series of steps, right? So this is the series of steps, right? So the UNet is the one that's actually taking that step. And the UNet itself, right, which actually I have a nice little picture of a UNet here. So this is what a UNet looks like. This maybe gives you a little bit more of an idea why it's called a UNet. So this is an older UNet. This is using convolutions, but you put the image here on the left and then the output on the right. In the original UNet, they were using this for segmentation, but in the Stable Diffusion UNet, right, this is just going to be a latent on both sides of that. So it's not going to be a image and a segmentation map. It's going to be basically one latent and then a different latent on the other side, right? But you can see here how basically it goes from very wide to very narrow and then back to very wide. So that going from wide down to narrow down to wide, that is that U shape, and that's where the name UNet comes from. Okay, so now we have the UNet inside the latent space of this diffusion model, which generally refers to all of these. And you can see here this arrow here, which says conditioning. And this conditioning kind of comes here, and you can see how this stuff is going into each part of this UNet. So the UNet, in addition to getting the latents, right, it's also getting a little bit of extra information, which is called this conditioning. And this conditioning can be anything, right? So it can be a semantic map, which is just like a segmentation map. It can be a piece of text. It can be images. It can be whatever you want, right? And then obviously you're going to have to kind of massage and train your model so that it can accept a specific type of conditioning. It's not going to be able to accept everything out of the gate, right? You have to explicitly train it to accept these type of things. But with this conditioning vector, you can effectively control the denoising, and then by controlling the denoising, you can then control the final image. So that is conditional diffusion models. So conditional diffusion models iteratively denoise from Gaussian noise at training time step t from 0 to n, right? So you're removing the noise over a series of time steps. Dependent on Gaussian noise, this is the noise that you're adding, is added to the original input signal to obtain a noisy input. So here's your x of t, which is your latent, or you could think of it as your image, right? And your image is getting some amount of noise. So here you're adding your noise to your image, right? And alpha t is the noise schedule, right? So that's I mentioned at the beginning that you're adding a different amount of noise or removing a different amount of noise depending on where you are in this process. N is the total number of diffusion steps. And we actually read a paper last week about how you can basically drastically reduce the number of diffusion steps by doing this, I forget what it was called, LCM, but basically it's a latent, I already forgot it, but starts with a C. Consistency, that's what it is. Latent consistency model. The diffusion model is trained on denoise by predicting either the noise or called the V prediction. I guess this is the image without the noise. The signal to noise ratio at the time step is given by this and decreases at as t goes to n. At inference, samples are generated starting from pure noise. Here you're starting from the normal distribution centered around 0 with a standard deviation of 1. That's what this fancy script n means. And denoising it. Note that at the inference time x of n has no signal, i.e. 0 SNR, which has significant implications for video generation as we describe. And here they're kind of setting up the actual trick that they end up using. So here in the abstract, right, they mention that they do a trick regarding the noise schedule. And we actually, what they're going to end up doing is basically they're going to put in a trick. Actually, why don't we just, okay, we'll wait and then we'll get into that, because what they're referring to here is the zero terminal SNR noise schedule. Maybe let's just get into it now. But we found that diffusion noise schedules used in prior work have a train test discrepancy which prevents high-quality video generation. At training, the noise schedule leaves some residual signal, right? And what they're referring to here is that there's a bug in diffusion model implementations where the very last step is not pure noise, right? So the very last step here, right? So here, when you're at this time step here, this here should be pure noise. X at time step t should be pure noise, right? But I forget what the name of the paper is, but we read this paper a while ago where people basically discovered this bug where actually at the very end it's not pure noise. It actually still has some vestige of the original image distribution in there, right? And they said, okay, well, if you make sure that it's pure noise, then you clean up, for example, some artifacts that could occur where the images tend to be a little bit more gray. They tend to have a little bit more to do with the image distribution that you would want them to. So here we have Meta basically realizing this and implementing that bug fix or that trick into their noise schedule such that you fix it. And that's the zero terminal signal to noise ratio bug in a noise schedule for a latent diffusion model. This prevents the diffusion model from generalizing at test time when we sample from random Gaussian noise with no signal about real data, right? So no signal. They don't want any of that original image distribution information to appear in the, or to be kind of stuck in there. The residual signal is higher for high-resolution video frames due to redundant pixels. We resolve this issue by scaling the noise schedule and setting the final alpha n0, or this alpha, which basically determines the noise schedule, right? So the noise is a factor of alpha, or there's an alpha in there. There it is. 1 minus alpha t sigma t. So this alpha t kind of controls the noise schedule. So by setting alpha t equals to 0 at the very end, then you basically make sure and guarantee that at that terminal state, it is pure noise, which is important, right? And machine learning is like filled with these kind of like little bug fixes and tricks like that where you can have everything right, and if you just have one thing wrong, it doesn't work. And if you fix that one thing, suddenly it all works, right? So that's kind of like par for the course in terms of machine learning model development. Okay. Now let's go into 3.2 here, emu video. We kind of sneaked ahead there, but let's read the rest of this. We factorize text-to-video generation into 2 steps. So I don't really like the use of the word factorization here. That kind of makes it more confusing. Factorization has specific math definitions, right? Like you factorize like maybe a polynomial, right? By breaking it up into sub-polynomials, right? But they're using factorize here just to generally refer to the idea of taking something that's multiple, something more complicated and breaking it into pieces. So that's the way that they're using the word factorize, but I feel like that just kind of makes it more confusing. Why is this so shit? Let me do this. There we go. That's a little bit better. I'm like kind of like cut off halfway through. Given the text prompt P and generating T frames, we implement both steps using a latent diffusion model F, illustrated in figure 3. We initialize F with a pre-trained text-to-image model. So they're not training from scratch. They're starting from a pre-trained text-to-image model, which I think is their own EMU model, right? So they're starting from this one here, EMU enhancing whatever. And if we actually take a little tangent here to read exactly what this one is. This is a little bit older. I think this was released in September, but basically this is like Stable Diffusion, but the meta version, right? So there really isn't that many different tricks. It's basically kind of about the same as SDXL. It's a latent diffusion model. It kind of has all the same stuff, but it's trained entirely from scratch by Meta so that they can have their own thing, right? A lot of companies will use SDXL as the starting point and then fine-tune SDXL or any of these Stable Diffusion models. But if you're Meta, you don't want to be using somebody else's model, right? You have the amount of money, you have the expertise in-house to just train your own model from scratch. So that's basically what they did. So 1.1 billion image text pairs, that's the pre-training data set. And then a few thousand carefully selected high-quality images for fine-tuning, which apparently they said that supervised fine-tuning is actually quite important here, with a set of surprisingly small but extremely visually appealing images that can significantly improve the generation quality. So that's a trend, too, that we're seeing more and more, where being extremely careful about that fine-tuning data set is very important, right? So in your pre-training, you kind of want to throw the whole kitchen sink at it, put every single image text pair that you can ever find, right? And even start generating your own synthetically. But when it comes down to the actual fine-tuning part of the training pipeline, then you want to be extremely careful about the fine-tuning data set to the point that you have people manually going through that data set many, many times and making sure that every single example is perfect. So that is EMU, pretty high quality. You know, it's kind of hard to get impressed by text-to-image models at this point. They all kind of feel like they've gotten to this kind of S-curve point where they're all pretty much about as good as you could expect them to be. So that's what they start from, right? They're not going to start from something from scratch. They're going to start from an already pre-trained model, so they're starting from that one. Initializing F with a pre-trained model to ensure capable of generating images. Thus, we only need to train F to solve the second step, i.e. extrapolating a video condition on a text prompt and a starting frame. We train F using video text pairs by sampling a starting frame I and asking the model to predict T frames using both the text prompt and the image conditioning. We denote a video V consisting of T video frames, height and width, 4D tensor of shape T times 3 times H times W. So, right, we were just saying that images are 3-channel images. 3-channel images are 3 by height by width, and a video is basically a T, as in T total frames, by 3 by height by width. Since we use the latent diffusion models, we can first convert the video into a latent space. So you see how here in the latent space, you still have the same number of T. You possibly have a different number of channels, and you actually for sure have a different number of channels, and then the H and W are going to be smaller, right? So kind of the whole point of latent diffusion models is that this here, 3 times H prime times W prime, which is the original size of the image, is way bigger than this, C times H times W, right? So C times H times W is going to be smaller. It's going to be these little like latent images. The latent space can be converted back to pixel space using the autoencoder's decoder, right? So that's this problem here, right? In pixel space, this is the 3-channel, big width, big height. Latent space, more channels, smaller width, smaller height. So in order to go from pixel space to latent space and from latent space to pixel space, you use the encoder and the decoder. The T-frames of the video are noised independently to produce the noise input XT, which the diffusion model is trained to denoise. Okay, so this is kind of interesting. Each frame of the video is noised independently. Okay. So whenever they're training it, right, they're adding noise. So that's saying that in the training process, they have, I guess, videos, and then they say for each frame of the video, they're going to noise it independently. We condition on the starting frame I by concatenating it with the noise. Okay, so they're conditioning it they're conditioning the removal and the adding of noise at each individual frame of the video, right? So here the conditioning, and they're conditioning it on the video or on the image itself. So you're conditioning the noise removal and the noise adding on one of the frames, basically, ideally the first frame. So our design choice allows the model to use all the information in I, unlike other choices that lose image information by using a semantic image embedding for conditioning. Okay, so what are they referring to here? Is that, Jesus Christ, I changed my mouse and now it's a little bit more complicated. Lose image information by using a semantic image embedding for conditioning. Okay, so what is a semantic image embedding? A semantic image embedding is an image embedding that, an image embedding is basically a compressed form of the image, right? It's a little vector that represents the image, and you can think of a latent image as a type of image embedding, right? A semantic image embedding is a compression of the original image, so you're going to be losing something, right? Whenever you go from this X to this Z, you're losing a little bit of information. Now, if your encoder and your decoder are good, you're not going to be losing a lot of information, right? Because the information that you kind of cut out with your encoder, you're going to kind of gain when you decode it. But what they're saying here is that you don't want to be taking your image and compressing it into some kind of latent representation and then conditioning on that image embedding. Even if that image embedding maybe is better for semantic tasks, right, where you actually need to understand what's in the image and you don't necessarily care about all the details in the image, right? Because that's often what you're losing with your encoder. You're losing the details, but you're kind of strengthening the actual semantic information in that image, right? They're saying don't do that. Instead, just conditioning it on the full image, because if you condition it on the full image, it'll have more of that information, because really what you want is for all of the stuff to work, right? If you don't want to lose the background, right? When you're doing a video, if you compress this image into some kind of image embedding, you're probably going to lose all this detail here, right? All this like background detail, because the encoder is going to be like, well, I don't give a shit about this background. What I really care about is telling you that this is a robot on playing the DJ thing, right? So I think that's a nice little realization there, that, hey, maybe don't compress the image if you're going to use it to condition each frame of the video, because each frame of the video should have ideally a lot more kind of like low level, like pixel space almost, information that is consistent with the original frame. Okay. We represent I as a single frame video, t equals 1, and 0 pad it to obtain a t by c by h by w tensor. We use a binary mask m of shape t by 1 by h by w. So binary mask, right? Either 1 or 0. So that's why this C channel basically just became 1. That's where that dimensionality drop comes from. That is set to 1 at the first temporal position to indicate the position of the starting frame, and 0 otherwise. The mask M, starting frame I, and the noise video XT are concatenated channel-wise as the input to the model. Damn, okay. That means it's going to be kind of a big diffusion model, right? Because you're doing it basically all of the channels at once, right? Which is kind of interesting, because this latent diffusion model, right? This UNet is acting on this latent, and that latent is kind of small, right? It's basically just the reduced height, the reduced width, and then the channel dimension. But now they're saying that, okay, we're actually also concatenating every single channel dimension of every single frame in this video into that. So in fact, the denoising UNet here is actually, it's not just consuming one latent, it's consuming the whole video of latents, which is going to be a really thick stack of latents. So this might actually take a lot more memory than a normal diffusion model. We add new learnable temporal parameters, a 1D temporal convolution after every spatial convolution. So here, what are they referring to is that temporal convolution, right? In a convolution, generally you're convolving across the spatial dimensions, but you can also convolve across temporal dimensions. So do we have anything here? This is WaveNet, so this is like kind of an older, very old audio model, but actually this isn't really explaining what I want at all, but effectively you're just convolving across the temporal dimension, which in this case is going to be the number of frames. Yeah, none of these are particularly good. The original spatial convolution and attention layers are applied to each of the T frames independently and are kept frozen. Okay, so they're taking the diffusion model, right, and they're basically keeping most of it frozen, and now they're really only pushing gradients into these extra layers which they added, which are these spatial convolutions in the time dimension or temporal dimension. The pre-trained T to I model is already text conditioned and combined with the image conditioning described above. F is conditioned on both text and image. Okay. Then you get the zero terminal SNR noise schedule bug fix, which we already went into, and then let's go into here, interpolation model. Also, if you guys have any questions, feel free to interrupt, right? Sometimes I feel like I'm just kind of sitting here blasting through this paper and I don't know if anybody's understanding anything or if everybody's just kind of like quietly nodding along, right? Let's get a little robot wave to hype up the crowd. Let's do another one. Action. Greet. That's right. Wave at them, buddy. Wave at them. He has a question. It's not a he, though. It's an it. Right? Greet. Greet at us. Talk to us. Okay. Interpolation model. We use an interpolation model I, architecturally the same as F, to convert a low frame rate video of T frames into a high frame rate video of TP frames. Okay, all right, so this makes a little bit more sense. So initially here, when they were like, we concatenate the channel-wise as the input to the model, I was like, that's going to be a shit ton of stuff to feed into this diffusion model. You're going to literally feed the entire video into this? That's absolutely insane. But here we have our answer as to why it's not insane, is that actually they're only feeding it at a much lower frame rate. So they have basically kind of similar to SDXL. So SDXL is kind of like, has a two parts, has like basically the full model, which generates the image at a small resolution. Then they have this kind of like upscaling type model, which will upscale and make the image bigger, right? So kind of a similar idea, obviously different because it's not upscaling the image. In this case, it's increasing the number of frames. So it's like upscaling in the frame rate. So interpolation model I. Convert the low frame rate video of T frames into a high frame rate video of TP frames. The interpolation model operates on TP cross C cross H by W inputs. For frame conditioning, the input T frames are zero interleaved to produce TP frames. So this is basically saying that they take the original smaller frame rate and then they interleave basically 0 frames in between and then they run it once more. Binary mask indicating the presence of T frames are concatenated to the noised input. The model is trained on video clips of TP frames, of which T frames are fed as input. For efficiency, we initialize I from F and only train the temporal parameters of the model I for the interpolation task. Okay, so kind of tricky, to be honest. You know, they're starting from a text-to-image diffusion model. Then they're keeping that frozen. They're adding temporal convolutions and then feeding in a low frame rate version. And then they're going to create a new model from that basically is mostly frozen except for those temporal convolutions that they added. So they're going to end up with 2 different models here. Or actually, they could really just end up using this model. So it's actually might be like a multi-step process here, but then they really only use this interpolation model at the very end? Maybe not. Josh Phillips. Sounds like this paper is essentially just generate an image and use an image to video model to animate it. The 9-channel UNet is interesting. Animate diff uses 8 channels, I think. Yeah, it's basically that. It's basically just adding more channels into the UNet and then just, I guess that's what videos are anyways, right? Videos are basically just images with more channels. Emu video can be trained using standard video to text datasets and does not require a deep cascade of model. Maybe one thing to talk about here is that video text datasets are kind of trash, right? Like, sure, we have YouTube, but like, I feel like we need the next version of that, right? We need this. We need the, like, here they're talking about the 1.1 billion image text pairs. Where's that for video? Where's that for video text? And Facebook is sitting on that data set, right? They literally have that. That's what Instagram is. That's what Facebook is. They have probably more data than anyone in terms of like, here's the text description of an Instagram video, and then here's an Instagram video. So I don't know why they're not using that data. It seems really obvious for them to use it. Maybe there's like legal implications or something, but at inference, given a text prompt, we run F without the temporal layers to generate an image. We then use I and the text prompt as an input to F to generate T video frames directly at high resolution, and then we can increase the video FPS using I. Okay, so it's a multi-model pipeline here. So you're going to use your text-to-image model to generate the image. Then you're going to use this F, which is the kind of like low frame rate model, to generate basically the video but at a low frame rate. And then you're going to use the T to act, or not the T, the script I, this one, to interpolate between them. So it's like if you wanted one final video that has all of the bells and whistles, you're basically going to have to go through 3 separate diffusion models to do that, which is kind of intense, right? Because that means that if you're trying to run this locally in your house, you can probably run the text to image model, but the low frame rate run is probably going to already be pushing the boundaries of your VRAM that you have at home, and then for sure the interpolation model is going to be even more insane in terms of the total amount of memory you need to even run it. This comes at no additional training costs that do joint fine-tuning on image and video data to maintain such style. Many direct T2V approaches also initialize from a pre-trained T2I model and keep the spatial layers frozen. However, they do not employ our image-based factorization and thus do not retain the quality and diversity in the T2I model. Okay. Robust human evaluation, aka the juice. Similar to recent studies, we find that automatic evaluation metrics do not reflect improvement in quality. Yeah, I'm kind of 100% on this train. I think that automatic evaluation accuracy, these kind of like quality metrics like LPIPs and Frichet, inception distance, like those are all basically garbage, and I think that you're going to need to do human studies where humans kind of evaluate. But I do think that maybe there's opportunities to improve that, and it seems like that's what this juice is. So what are they doing here? So you have to basically pick, but then you pick, and then you also decide which one. Video generates quality in the alignment and faithfulness, so Q and F. We found that asking human evaluators to justify their choice, and I guess this is where the word juice comes from, 1, when picking a generation over the other significantly improves the inter-annotator agreement. The annotators select one or more predefined reasons to justify their choice. The reasons for picking one generation over the other are pixel sharpness, motion smoothness, recognizable object scenes, frame consistency, and the amount of motion. Okay, so how long until we have visual language models doing this for us, right? Because we saw how in the language model space, one of the actually most common ways that people evaluate the output of language models is using a different language model. So they will literally use something like GPT-4 to evaluate the answers of other models, right? So they'll have like a Llama 2 outputting something, and then they'll have like a Mistral output something, and then they'll have GPT-4 say, which answer did you like better? So I wonder if that's where text-to-video and text-to-image models are going, where you're going to basically use GPT-4 vision, and you're going to feed it 2 images, and you're going to say, which one do you like better? And it's going to say, I like this video. I like image A better, or I like video B better, right? So that's kind of interesting. Where do we think evaluation of images and videos is going? Is it going to actually just be AIs evaluating AI-generated TikToks? Rotten Tomatoes GPT, perhaps? Okay. Implementation details. Provide complete implementation details in the supplement appendix A. Okay, so you love to see it. This is the open source AI that Meta does, that OpenAI should have done. But look at this. This is beautiful. They're basically telling you all the different little hyperparameters, all the different little tricks here. You can even look at this. Have the optimizer, betas. All of these look relatively learning rate, constant learning rate. So no schedule for the learning rate, which sounds weird, but then if you remember, they said that they start from that pre-trained diffusion model, and they're basically keeping most of it frozen, right? The only things that they're really pushing gradients into are those little extra layers that they added for the temporal dimension. So they might not even have to train this for that long, right? So these are kind of smaller learning rates, but they're really only training those little extra layers, so they don't need to do much more fancy stuff. It's really small, big batch size, small batch size. Training F. Okay, so this is the super resolution one, and this is the F. So one way to tell how big a model is to look at the batch size, right? So whenever the batch size is small, that means the model is probably very memory intensive, right? So here, this high quality FT, which I think is the one that generates the course, has a much smaller batch size than this one here, the I, which actually tells me that the I is somehow smaller than this one, which is kind of weird. That's not intuitive. That's not what I would have thought. But compared to here, right here, this one, 512, much bigger batch size, which means that these models are probably smaller, or the memory that they take on your GPU to run them, which is correlated to the amount of memory it takes on your GPU to train it, right? If it takes a lot of memory to train, it probably takes a lot of memory to run, and vice versa. Okay. Let's go back. We adapt the text-to-image unit architecture from their original EMU paper, right, this one, and for our model, and initialize all the spatial parameters with the pre-trained model. The pre-trained model produces square 512 pixel images using 8-channel 64 by 64 latent. So this is the thing that I said is smaller, right? So 8 by 64 by 64 is smaller than 512 by 512 by 3 is basically the way the math works out. As the autoencoder downsamples spatially, the model used both a frozen T5XL and a frozen clip. So this is the text encoder that basically converts the text, right, that's being used to condition the model into a latent, or like a little embedding or a little vector that represents the semantic meaning of that text, right? And they're using clip for that, which is pretty standard. Pretty much everybody uses clip. Separate cross-attention layers in the unit to attend to each of the text features. After initialization, our model contains 2.5 billion spatial parameters, which are kept frozen, and 1.75 billion parameters, which are learned. So this is a lot. Okay, maybe not. So the original model, the original text-to-image model has 2.7 billion spatial parameters. That's not the full thing, though, right? That's just this part here, the denoising unit. If you want to run this whole pipeline, you still need this encoder and the decoder, and then you also need the text encoder. So this is not all of the weights that you need, but kind of interesting how the extra layers that they add, these temporal convolutions here, are actually quite significant. It's not like just a little bit of extra on top of the original diffusion model. It's like significant. It's like almost like the same size. It's like you're doubling the amount of parameters there. Temporal parameters are initialized as identity operations, identity kernels for convolution, and zeroing the final MLP layers of the temporal attention block. So this is actually similar. The ControlNet paper did this. So ControlNet is not quite like this conditioning, but it's similar, right, in that you're basically trying to control the output of a pre-trained diffusion model with some specific input. In the case of ControlNet, it was things like canny edge maps, segmentation maps, things like that. But I remember from that ControlNet paper, one of the tricks that they did is that they also had this problem of like, okay, we need to add a little extra module. How are we're gonna freeze everything else, but this little extra module, how do we basically initialize the weights in that? And we're basically gonna initialize them from 0. And it seems like they did the same thing here, right? They're initializing these extra temporal parameters with either basically 0 for the multi-layer perceptrons and then identity kernels for the actual convolution that kind of maps across the time dimension. In our preliminary experiments, identity initialization improved the model convergence by 2x. For additional channels, in the model input due to the image conditioning, we add C+1 additional learnable channels to the kernel of the first spatial convolution layer. This is kind of crazy. Okay, so they're not just adding extra temporal layers, but they're also adding one extra channel to the spatial convolution stuff. So it's like, that's kind of interesting too. I wonder why they felt the need to do that. That's a little bit of extra complexity, but it kind of worked out, I guess. Our model produces 512 pixel square videos of 8 or 16 frames and is trained with square center crop video clips of 1 to 2 or 4 seconds. Is that the Instagram data set that I'm talking about? They just are too afraid to say that it's Instagram? I don't know. I'm actually not on Instagram, so I don't know. Is that kind of on par with what you would expect? 1 to 2 or 4 seconds of square center crop video clips? Efficient multi-stage, multi-resolution training. To reduce the computational complexity, we train in 2 stages. For the majority of training iterations, 70,000, we train on a simpler task, 256 pixels, 8 FPS, 1 second videos, which reduces per iteration time by 3x. Let's do 2. 3. Which reduces performance time by 3.5 due to reduction in spatial resolution. And then we train the model at the desired 512 pixel resolution on 4 FPS, 2 second videos for 15K iterations. Okay, so I think this rhymes with the SDXL as well. I think SDXL also did this, where they train smaller resolution and then they train bigger resolution. And here, because they keep most of it already frozen, right? They use that pre-trained text-to-image model, they freeze it, they add extra layers. It's interesting to see that same trick of starting with lower resolution then going to higher resolution also works if you're just training extra layers, but the amount of extra layers here is significant, right? It's like almost like the same size of same number of parameters, so maybe that's why the trick keeps working. So much alchemy going on here in machine learning. Why they still use convolution? Is it a small part of it? So convolution works well in the temporal dimension for sure, right? Because in the temporal dimension, you want the kind of like, you don't want all of it to be there, right? So if you used something like a transformer, right, the transformer, every part of the sequence pays attention to every other part of the sequence, right? So the entire video would pay attention to the entire video. But convolution, it's only a small neighborhood around a specific frame that is basically part of that convolution, like, area of impact, if you want to think of it that way. I think there's like a fancier terminology for that. So when you're making a video, you don't necessarily, like, some information from further away frames matters, but mostly what you want is that each frame is consistent with the frames that are right before it and right after it in a very constrained point in time, right? And we saw in other text-to-video models how they kind of over-engineer this, right? And they usually have maybe 2 different terms. They have like a way to have information from far away things impact, and then a way to have information from nearby frames impact. But by using a convolution that is limited to a specific number of frames and then convolves across that time dimension, I think that's a very simple way of making sure that only local frames are kind of impacting each other in that way. I don't know if that kind of made sense. Hope that answers your question, Liu. But I think it's more simplicity rather than simplicity and total amount of compute and memory required, rather than necessarily it's the best solution. I'm pretty sure if you didn't use a convolution and you had the magic giant GPU from the 2030s, if you used just a giant self-attention for every single frame and every single frame, it would probably work better, but we don't have that magic GPU from the 2030s yet, so we have to come up with tricks that allow us to reduce the total amount of compute, and a convolution over the temporal dimension is a way to do that. Although the frozen spatial layers were pre-trained at 512 pixels, changing the spatial resolution at inference to 256 led to no loss in generation quality. We use the noise schedule from 256 with a 0 terminal SNR for 512 using the V-prediction objective with n equals 1,000 steps for the diffusion training. This is monstrous. 1,000 steps? That means it's 1,000 steps like this. That's a lot of steps. We sample from our models using 250 steps of the DDIM sampler. Optionally, to increase duration, we further train the model on 16 frames from a 4-second video clip for 25K iterations. Okay, so they go from 256, 8 FPS, 1 second, to 512 by 512, 4 FPS, 2 seconds, and then the final magic training recipe here is 16 FPS for 4 seconds. So this is like a 3-part training pipeline here with all this extra stuff that they're doing here, where they first train the text to image, then they train this the first model, which they call F, and then they train the interpolation model. So quite complicated training setup here for sure. We find that the motion of the generated videos can be improved by fine-tuning the model on a small subset of high motion and high quality videos. Okay, so further fine-tuning. We automatically identify a small fine-tuning subset of 1.6K videos which have a high motion, computed using motion signals stored in H.264 encoded videos. So H.264 is like a human-designed encoder. So this encoder here, right here, the encoder and the decoder, these are learned, right? These encoders and decoders, you learn them through the process of gradient descent on a huge data set. So they're not very human interpretable, right? I don't really know what the fuck this Z is, right? It's just like a bunch of numbers, but it's like basically the magic machine learning process has created this encoder. But H.264 is not that. H.264, which is what, I don't exactly know if Netflix uses that, but like Netflix, like any of the like video that you see like in actual products, especially products 10 years ago, they're using that, H.264. It's a hand-designed, human-created encoding format, right, where the whole point is to reduce the dimensionality of that video data so that you can send it over the internet to your computer, and then you can H.264 it back into the full video. But H.264, the way it kind of works is it's basically saying this part of the image is the same, and then for the next 10 frames, this part of the image is the same, right? So it's basically kind of like leveraging the fact that parts of the video are going to stay the same. So one way of identifying which videos have a lot of motion is to look at the H.264 motion signal and say, okay, if the H.264 is saying I have to constantly I can't compress this video very much because the pixels in the background are constantly changing, that's probably indicative of a video where the background is constantly changing, and that's how they can automatically identify from their training data set or fine-tuning data set, holdout, which of the videos are worth using for this fine-tuning, where you're specifically fine-tuning for the purpose of high-motion videos. We follow standard practices and also apply filtering based on aesthetic scores and clip similarity between the video's text and the first frame. Holy shit. Okay, so this is a lot, so much complexity. So not only is the model pipeline itself kind of complicated, they have a couple different models that they're training, but the training pipeline for each of those is complicated, right? They have different pre-training occurring at a different resolution, different frame rates and stuff like that. And then the fine-tuning is done with a bunch of automatically created fine-tuning data sets that are based on weird things like the H.264 motion signal, aesthetic scores, and then clip similarity, which is basically using the clip model, right, which will take an image and project it into some embedding, right? And then the clip similarity is basically how close together are those two vectors for those two images, and specifically the first frame, and then in this case it's not even an image and a image, it's an image and a text, right? And that's the magic of clip, is that you can compare a piece of text and an image. We initialize the interpolation model from the video model F. Our interpolation model takes 8 frames as inputs and outputs 37 frames at 16 FPS. So that's not actually that great, to be honest. I think that we still have some ways to go. I feel like 30 FPS is kind of like the standard for video, 60 FPS is probably like cinematic. I kind of like vaguely recalled that the Lord of the Rings prequels, The Hobbit, was 60 FPS. And then I think that people who are like professional gamers, right, who play video games professionally, they kind of like get monitors that are specifically like 200 FPS. So once we get to 200 FPS, I think that's the kind of limit of human quality where it doesn't really matter anymore, but 37 frames at 16 FPS still feels like we got some room to improve. Add noise to the frame conditioning, randomly sampling time steps. At inference time, we noise augment the samples from F with T equals 100. Okay. So right about the middle, they add more noise. Pretty cool. Okay. So we got other papers to read here, so we're going to kind of skip through the experiments here, right? The experiment section, they're just going to be basically doing some ablation studies. Maybe let's read some of that. We use the text prompts from prior work to generate videos. The prompts cover a wide variety of categories that can test our model's ability to generate natural and fantastical videos. Okay. Factorized versus direct generation. We compare a factorized to a direct T2V generation model that generates videos from text condition only. The factorized generation model's results are strongly preferred in quality and faithfulness. The zero terminal noise schedule bug, multi-stage, multi-resolution training, and then high-quality fine-tuning. Okay, so those are the different things that are going to be ablating. So Q and F are the two scores, right? Quality and then faithfulness, and then I think higher is better. So multi-stage, HQ fine-tuned, frozen spatial. This one seems the best. The preference on adopting a design decision versus a model that does not have it. So 0 SNR seems to be the most obvious thing that you want, but all of these are above 0 or above 50, which means that every single one of these tricks that are part of this paper did contribute to the final quality, right? So what they're basically saying here is that if one of these numbers was below 50, it means that people preferred it without the HQ fine-tuning, or people preferred it without the multi-stage. So the fact that all of these are above 50 means that all of those different tricks that they just described did make the model, or did make the final quality higher, so they're worth implementing. Tested freezing the parameters, comparisons to prior work. Look at that, you got some ships in the rain. Low angle pouring beer. Where's Will Smith eating spaghetti? Because that's really the benchmark for video quality. Okay, we'll come back to this, but we're already 1 hour into this, and I do want to get to the to this model here, the emu edit, because I think this one has an interesting little tidbit. So I'll pause there if you guys have any questions, and then we'll get into emu edit. Let's get a little robot wave. Let's do another one. Wave for us. That's right. Okay. So emu edit, precise image editing via recognition generation task. There's also a little bit of a story here. So maybe one thing that you notice here is that it's not necessarily the same exact group of people. So you see here, it's Ishan Mishra and then like this group of people. And then you look at this one, it's a different people, right? So you got different groups of people working on the emu edit than you do the emu video. So that's kind of cool, right? And then this is like the combination of everyone, I think. But it means that within Meta, right, they have so much money, and being a big tech company, that they can have literally groups of like 10 people that are working on the same exact model, but just different applications of it. One for video and then one for kind of this editing, which we'll see here, right? This is when you want to basically do text to image, but the next version, the next generation of text to image. The next generation of text to image is called instruction-based image editing. And this is what you see with DALL-E, right? So DALL-E 3. So in ChatGPT, if you open up ChatGPT, right, the way that DALL-E 3 works, it's not like old school Stable Diffusion where you just type in your prompt and it generates the image and that's it, right? You can basically kind of interact a little bit more. It has this kind of like chat base, the same way that you have instruction fine-tuning for chatbots that turns them into these kind of like chatbot type, like they respond, you answer, they respond. You can do the same thing with a kind of an image workflow. So that's what instruction-based image editing is. It enables users to perform any editing operation using a natural language instruction. However, current models in this domain often struggle with accurately executing user instructions. We present EmuEdit, a multitask image editing model which sets state-of-the-art results in instruction-based image editing. To develop EmuEdit, we train it on a multitask across an unprecedented range of tasks such as region-based editing, freeform editing, computer vision tasks, blah, blah, blah. To enhance Edit's multitask learning capabilities, we provide it with learned task embeddings which guide the image generation process. Both these elements are, we're going to go into what these learned task embeddings are. Essential for EmuEdit's outstanding performance, we show that EmuEdit can generalize to new tasks such as image inpainting, blah, blah, blah. This capability offers a significant advantage in scenarios where high-quality labeled samples are scarce. To facilitate a more rigorous and informed assessment, we release a new challenging and versatile benchmarks that includes 7 different image editing tasks. My blue screen is way better now. Did I do anything? I don't know what you mean by blue screen. Do you mean green screen? I don't know what you're talking about. Image editing, blah, blah, blah. Okay, so we're going to skip that introduction. We're going to go to the bottom of the introduction. Here we go. In summary, this work addresses the limitations of instruction-based image editing. We demonstrate that by employing multitask training, we can enhance our model's performance. By incorporating learned task embeddings into our model architecture, we not only improve its result, but also enable efficient few-shot learning. With these improvements, our model sets a new standard. Related work. Okay, this is going to be more crap. Multitask dataset. Training a robust and accurate image editing model requires a highly diverse dataset of input images, editing instructions, and output edited images. However, manually collecting is impractically time-consuming. Existing sources on the web are limited in size. Therefore, we construct a new dataset that encompasses 16 different tasks and 10 million examples. Okay, so each example contains basically like a 4-tuple here. You have 4 different things. You have an input image X, or input image CI, text instruction CT, target image X, and a task index I out of 16. The following section outlines the process. Task categories. Okay, so basically region-based editing, freeform editing, and vision tasks. So they're kind of being more explicit about the different tasks that you would need to do things, right? So like, for example, here you have a cat. If you want to remove the tail, what does that consist of, right? Well, you probably need to segment out the tail, keep everything else the same, and then just do kind of region in painting, right? Add a pink jacket. That's probably not going to require a mask because you do want to change a bunch of things. Make it rainy. Maybe for the rain, you segment a specific thing, right? Like, so when you're doing instruction editing of an image, really what you're doing is you're kind of performing one of 16 possible different tasks. And that's kind of what they figured out in this paper is they're like, okay, well, can we represent that task in some way, right? Do we basically have like a hard-coded flow where we say, okay, if you want to do this type of editing, you're going to use this model and this model and this model and this model and this model. But they do something more clever, which is creating this learned task embedding, right? And I do want to have like a little bit of a call out here because I feel like this is something that is kind of a coincidence that's a little bit too intense to not call out. So when I was working at Google, I worked with a guy called Carol Hausman. And this guy, he now leads, I think, the robotics group at Google, but he was known for this paper called Robot Skill Embeddings. And in this paper, he basically, he had robots that were doing a bunch of different tasks, right? So picking up a block, moving a block over a thing, moving a block around a barrier, moving a block from the floor to the table, right? And he created basically an embedding space for tasks, right? Given a specific task, you would create kind of like similar to how you create a latent space for, like Clip creates a latent space in which you can project both images and text, and you end up with little vectors that represent that image and represent that text, right? And you can do cosine similarity in that space between two different vectors. You can look at the distance between those vectors, right? That embedding space is the embedding space's images and text, right? But you can also do the same thing with something like a task, right? So you can basically create an embedding space that, rather than representing the semantic content of an image or the semantic meaning of a text, you can represent a task with this little vector that represents what that task is in kind of an abstract semantic way. It's not easy to interpret as a human, right? Like you can't look at an embedding vector or and say what is this task, but if you project enough tasks and shape that embedding latent or that task latent space with enough kind of gradients and tasks, over time you can basically interpolate between these tasks, and you can figure out what task you really want to do that is some weird combination of tasks that you have more explicitly mentioned. So I don't feel like I explained that super well, but that's basically what this paper is basically they said, hey, rather than instruction-based editing, really there's only 16 different tasks, which are some combination of like segmentation or like they require slightly different steps. Why don't we learn a task embedding which describes that task so that whenever the user says, hey, I want to do X, right? What we're doing is we're taking that, hey, I want to do X, turning it into some kind of task embedding and then conditioning the model on that task embedding, right? So the same way that you would condition a diffusion model on a segmentation map or a piece of text, you can condition it on this learned task embedding, which represents what you actually want to do with the image, which is add a pink jacket, make it rainy, blah, blah, blah. Right, so very cool idea, and I had to call out one of my kind of OG mentors because he was onto this idea way back in the day. I think this is like a 2018 paper, something like that, but pretty badass. Okay. Dataset is composed of tasks, which are divided into three main categories. Instruction generation. To generate, we leverage the dialogue optimized Llama 2 variant. So they're using a text, a language model to generate the instructions. So actually, this is pretty common now, right? Using language models to augment the text part of any kind of training pipeline or image pipeline. What are we doing? One is yellow. We observed that using a single agent to generate the instructions for all tasks leads to a lack of diversity in the dataset. Notably, the LLM exhibits a bias towards particular tasks and instructions phrasings. We utilize in-context learning to create a task-specific agent for each task. Concretely, we provide the LLM with a task description, a few task-specific exemplars, and a real image caption. We expect the LLM to output an editing instruction, an output caption, and which object should be updated. Our aim is to generate pairs of image and edited images that adhere to the edit instructions. We first detail our core improvements, blah, blah, blah. We describe post-processing, grounded, precise editing. A crucial prerequisite when creating a pair of input and edited images. So you're creating this pair of like, this is the original image, this is the user instruction, and then this is the edit image, right? Green screen. Darshan K asking me Altman. I don't know. Do I want to go into the whole OpenAI fiasco? Like, do you guys want to hear that? Do I want to hear my shitty take on it? Probably not, right? I feel like my take is garbage. Rely on prompt-to-prompt to build image editing dataset to support local edits. P2P additionally approximates a mask of the edit part based on cross-attention maps. P2P relies on the word alignment between the image and edited image caption to produce editing image pairs. However, when there is no word-to-word alignment, the resulting masks tend to be imprecise due to its reliance on cross-attention maps. Furthermore, as word-to-word alignment is not a practical assumption in most of the image editing tasks, this approach often fails to preserve structure. To address this, we propose a mask extraction method, which is applied, identifying the edited areas, creating corresponding masks, and then integrating these masks during the editing process. So this is another thing that we kind of see over and over again, is that these diffusion models, they're being optimized in such a way that they don't care about the cleanliness of the masks, right? Like they're not super anal about the like exact edges of objects inside the image, because they're not super interested in that, right? They just want to create like really cool looking images. Versus like if you were to look into the segment anything model, which is a model that's specifically for segmentation, the inside those attention and cross attention blocks within that segment anything model, it's much more rigorous and kind of precise about the exact edges of the segmentation and the exact edges of like, this is one image, this is a different image. So this kind of smells like that problem to me, where they're saying that like, hey, these masks aren't very super clean inside the whatever diffusion model they're talking about here. Okay. Hoopo OpenAI rants are part of my cultural identity. Here's a little, let me start this OpenAI rant with this. So instruction-based image editing models like Instruct Pix2Pix are designed to process any given instruction. They often struggle to accurately interpret and execute such actions. Okay, so Instruct Pix2Pix is this. Instruct Pix2Pix came out in the 18th of January 2023, and it's basically the proto version of Emu Edit, right? They don't have task embeddings, so they don't have this part yet, the learn task embeddings, but they basically do a lot of the same things. They kind of like use GPT 3.5 to generate captions. Where is it? Right here. They create a data set of these triplets, edit instructions, input captions, and output captions, and then fine-tune the DaVinci model based on these, and then I think they generate some of these captions with GPT-3, generate text edits. So this was kind of like the cream of the crop image editing, or instruction-based image editing, right? And the guy for this, 18th January 2023, Tim Brooks. Look this motherfucker up on LinkedIn. Tim Brooks, look at this. January 2023, OpenAI. So this guy, who was at Berkeley, published this. This was the last paper that he published in Berkeley, and then he gets hired by OpenAI, and then OpenAI releases DALL-E 3, which basically does exactly this kind of like instruction editing. So this is DALL-E 3 is effectively what it is. Like DALL-E 3 hired him, and then he basically just re-implemented this with maybe a couple new tricks inside OpenAI. So this is the OpenAI guy. But I'm more curious as to what happens with this guy after all this fiasco, right? Because, all right, I'm about to get into it. But what has happened is that there's been a coup inside OpenAI where Sam Altman and Greg Brockman got pushed out. So there's a board of people, and they basically pushed out the faction of the board that they disagreed with. So some people have already left. I think a couple different other more engineering and different people who were part of that Sam Altman, Greg Brockman faction have also left. So we might see, I don't know where Tim Brooks stands. I don't know where people like Alec Radford stands. There's a bunch of pivotal people in OpenAI, the ones that are actually doing the works, like this Tim Brook guy. It's unsure which faction they're part of, right? But it seems like there was a rift, and now you're going to basically have a separation, and you might see basically a new Anthropic, right? So the same way that Anthropic originally splintered out of OpenAI, you might see basically a new type of Anthropic that's the splintered faction of Sam Altman and Greg Brockman. So the problem with this whole fiasco is that we don't know what the fuck is going on, right? We don't really know what is going on. So like, it could be the case that Sam Altman is the good guy. It could be the case that Sam Altman is the bad guy. It could be the case that Ilya is the good guy. It could be the case that Ilya is the bad guy. It could be the case that Ilya is just a pawn, and there's someone who basically controls through the other board members, right? Because we don't really know. A lot of people are pointing the blame at Ilya, but there's other board members there that are kind of a little bit sketchy, right? They're these kind of like very corpo people that are probably just pawns for some other power faction that we're not even aware of, right? So like, is it the case that those other people basically told the other board members to recruit Ilya so that they can have the majority to then push out Sam? And what is the reason that they're pushing them out for, right? This is kind of where the good guy, bad guy situation kind of gets more complicated, where if they're pushing out Sam Altman and Greg Brockman because Sam Altman and Greg Brockman wanted to make it more closed, right? More secretive, more private, then they're the good guys, right? Because, hey, they were trying to make it less OpenAI. But if it's the opposite, and Sam Altman and Greg were trying to make it more OpenAI, and the Ilya faction that succeeded are trying to make it more closed, more secretive, then we lost, right? Then OpenAI somehow got even worse, right? So we don't know yet. We don't know which of those is the situation, and unfortunately, we're probably never going to know, right? Like, I don't think they're ever going to say everything. So, I don't know. It kind of sucks because it's like, I wish I could know who's the bad guy and who's the good guy, but we don't know yet because we don't know what their motivations were, and I doubt they're ever going to tell us what their motivations were. But that's my opinion. If you're interested in arguing about this point or theorizing, definitely drop by the Discord because there's a nice little discussion going on. I want to see where Radford goes. Yeah, that's what I'm saying. Alec, that guy does all the like 3D Dolly stuff. This guy, Tim Brooks, does a bunch of the Dolly stuff too. So like, those are the people that matter. You know, like realistically, like the Sam Altman, like that guy doesn't really matter, right? That guy's skill set is actually quite generic. Like you can find 50 other Sam Altmans in the Bay Area, right? Like just go to any venture capital, any kind of startup investing kind of place, you're going to find 50 other people like Sam Altman that are very polished, very good at talking, know how to say things, know how to manage. But the skill sets of these very niche kind of technical people, of which someone like Ilya is, or of which someone like Karpathy is, those are much more difficult skill sets to find. So those are the ones that matter, right? So I don't know. Maybe that's not the rant that people wanted, but that's the rant that you're going to get because I'm going back to the papers here. I think you are up there with them. I don't know about that. I wish, dude. I wish they would hire me, you know, but no one gives a shit, you know, because I swear too much and I'm too much of a plebeian, you know. I'm just sitting here with my robot friends. Look at this. Look at this. What do you think about... See, I'm never going to join the empire. I'm going to create my open source robot back here, and I'm going to put a free open source vision model inside there, and I'm going to fine tune it, and I'm going to create AGI. And no one's going to be able to stop me. So I'm going to continue to publish all my code. I'm going to continue to sit here and review papers, and I'm going to continue to tell people all that I can and share as much knowledge as I can and be as open source as possible until someone fucking comes to my house with a gun and shoots me in the head because I'm dangerous to society. You know? They can't stop you. They can't stop you, you know? So who cares? Who cares about the politics? If you just keep releasing your code and releasing everything that you can and trying to be transparent and try to just help as much as you can, that's the best you can do. So don't worry about the politics. Just use your skill set for the maximum good, and they can't hurt you. You know, the empire can't kill everybody. Eventually, the rebel wins. Down with a man, rah, rah, exactly. Don't let them control you. That's what they want. They want to control you. Okay, we were in this paper, though. We got distracted. Let's see, where were we at? We were here. Method. Okay, let's look at the architecture a little bit. Our model builds upon the foundation set by EMU, which is outlined in 6. The EMU model is a two-stage approach that begins with a pre-training phase and concludes with a quality fine-tuning stage. Okay, so that's pretty standard. Pivotal aspect of the method is that the fine-tuning dataset is relatively small. So again, seeing this same pattern where the fine-tuning dataset must be of exceptional quality, often necessitating manual annotation. So that's time and time again, right? We're seeing this pattern where actually if you're working on a project, the most important thing you can spend your time doing is literally going over your fine-tuning data set and making sure that every single example is super clean, right? Which is not what a lot of people do. A lot of people, when they're doing machine learning projects, really what they're spending the time thinking about is fucking architecture and training pipelines. But like, it really seems like all you need to do is just focus on the data set and then you'll get most of the juice out. High-resolution image generation incorporated with a 16-channel autoencoder and decoder. So same, it's a latent diffusion model, has an encoder and a decoder. In the following section, we adapt the notation of 2, a large UNet with 2.8 billion parameters. That's the same one that they had in this paper, right? 2.7, that's what they said. 2.7 parameter UNet, 2.7 billion parameter UNet. Where is it? Right here, 2.7b spatial parameters, which is the same as this one. 2.8 billion parameters. I wonder where that extra 0.1 comes from. Okay, you have text embeddings from clip VITL and T5 triple XL, which is the same as this. Slightly different. This is T5 XL instead of T5 double XL, so slightly different situations. Substantial pre-training dataset of 1.1 billion images. Given the encoded latent of an image, right, you feed your image X into your encoder, you get that latent Z. The diffusion process generates a noisy latent ZT, right? T is the time step. Noise level increases over time steps to convert EMU into an instruction image editing model. We condition it on the image to be modified CI and the instruction CT. Okay, so very similar to kind of like language models where you're basically instruction tuning them into this chat-like behavior. These instruction editing models are basically the image version of that, right? Where you pre-train them on the just standard text-to-image task, but then you have this additional fine-tuning where you're basically doing this back and forth, like, here's what I want, here's the text to change it, here's the final image, right? The final instruction image CT. And here, I guess they are kind of showing you the quality difference between instruct pix to pix, which is basically their way of saying Dolly 3, even though Dolly 3 is like better than this because instruct pix to pix is January 18th, 2023, and this guy for sure, Tim Brooks, he's for sure done a bunch of work, so Dolly 3 is not just instruct pix to pix, it's instruct pix to pix evolved, right? The better version of that. So here they're kind of not necessarily comparing to that, but you can see just how much more high quality it is. Play a rainbow colored trumpet. You see how it keeps pretty much everything else exactly the same, and it really just adds that rainbow colored trumpet. Same thing here where the edits, it's kind of as they were saying in the beginning of this paper, right? It's confused. It's struggle to accurately interpret and execute such instructions, right? So it's not that the model is incapable of performing the edit. The problem is that the instruction, which is this text, is confusing to the model, right? It's not entirely clear how this instruction should change the image, which is where the task embeddings come in, right? Where you can say, okay, well, this is the edit for this this task, and this is the edit for this task, and this is the edit for this task, and we're going to create an embedding space that has all of the tasks in it. And then whenever you say, hey, make it play a rainbow colored trumpet, we're going to take that and we're going to project it into this embedding space of tasks, and that's what we're going to give the model. We're going to give the model, hey, this is the task that the users want, except we're not going to give it that task in just text format. We're going to give it that task in this embedding space, so it can be some weird interpolated combination of tasks, such as like, hey, for this rainbow colored trumpet, you need to keep the background consistent, maybe segment out just this part of the thing, and then just change that part of the thing, right? So it's like some weird combination of multiple different tasks. I appreciate the love, Khalil. Thank you. Minimize the following optimization problem. Here's your noise, except now you have this CT. So this is the like little triplet that they're talking about up here, right? This triplet or quad tuple data set, which has the input image, the target image, the task index, and then the text instruction CT. And this task index is basically a one-hot vector describing the task. So similar to the original paper here, right? Your task ID is the same thing as the task index, right? It's a one-hot vector where here's the 16 possible tasks, and then this is the one that we're providing in this example, and then we're going to project that into this embedding space and convert that task ID or task index or one-hot task vector into a kind of a more nebulous, latent task embedding that describes and can possibly describe combination of tasks, right? So pretty cool idea. CICTX is a triplet of instruction, input image, and target image. In practice, we initialize the weights of emu edit with the weights of emu, right? So very similar as the video one. New weights are initialized to 0. During inference, we perform classifier-free guidance on both image and text conditions. In our experiment, we use a scale of gamma I for image condition and gamma I for the text condition. This is the... I feel like it's never worth explaining classifier-free guidance because it's just more confusing and it doesn't actually really do much. But classifier-free guidance is basically this here. You see this switch, right? So sometimes when you're training, you feed in the conditioning, but then sometimes you don't feed in the conditioning, right? So you can basically say, hey, remove the noise if I wanted you to do this with this text, and then remove the noise without that conditioning. And then you can look at the difference between, okay, with and without the conditioning, what changed, right? And that's effectively what's going on with classifier-free guidance is you're basically saying, here's with the conditioning and without the conditioning, and then I have like a little extra parameter, which is this gamma parameter, which I can use to basically tune how much I want between those, right? So it's kind of like almost like a strength of like how strong do I want that conditioning to be. So classifier-free guidance is all about kind of giving you that little extra knob, which is this gamma. Furthermore, we apply a rescaling of the diffusion scheduler to achieve 0 signal-to-noise ratio at the terminal timestamp. So this group of meta AI researchers also read that paper that I forget what it was actually called, but we did do a video on it where basically you have to have 0 pure noise at the very terminal timestamp. It's crucial in order to avoid any mismatch. For more implementation, see blah, blah, blah. Learn task embeddings. Given the generation process towards a correct task, we learn an embedding vector for each task in the dataset. During training, given a sample from our dataset, we use the task index I to fetch the task embedding vector VI from an embedding table and optimize it jointly with the model weights. We do so by introducing a task embedding VI as an additional condition to the unit, right? So the task embedding, which is this little vector that's describing the type of task in some learned way, right? So that's kind of the magic there, where it's not explicit. It's not just a one-hot saying this is a region-based editing or this is a segment the background and then replace that, right? It's like some embedding that can represent a more nebulous kind of concept of what the task that you actually have to do is. We integrate the task embedding via cross-attention interactions. The cross-attention is pretty standard. That's kind of where you're putting in the conditioning here, right? It's the QKV. This is the query key and value matrices inside the self-attention or cross-attention, and that's where that signal is actually going in there. Optimization problem is updated to this. Expectation value for Y hat. Here you have your noise, and you have your little triplet here, your encoded image. Time step T. K is the total number of tasks in our data set. I think they said it was 14 or 16. And then Y hat is a quadruplet. They keep kind of mentioning the same thing over and over again. Task-specific conditioning arises from the observation that models lacking such conditioning can become perplexed about the type of edit required, particularly when the instructions are complex or the edit type is ambiguous, right? Which is exactly the same reasoning that Carroll had here in his original paper. I don't think he's referenced in this paper, so I'm kind of trying to give him credit because I feel like he came up with this before anybody else. So Obviously, it's in a different field. It's in robotics, but you got to get credit where credit is due. Might opt for segmentation when a global edit is necessary. It would implement a style edit in situations where a local edit would fit better, right? So they're kind of like hypothesizing that the reason these models don't work well is because they're basically confused about exactly what you want. Whenever it says turn into a still from a Western, the model's like, okay, well, what do you mean? Do you want it to look like a Western? Do you want me just to change the face of this guy to look like the face of someone from a Western? Do you want the same hat? Like, do you want, like, you know what I'm saying? It's kind of, you can kind of feel for the model where you're a little bit confused about like what exactly you need to do out of that. Make his jacket out of leather. That one seems a little bit more obvious. In the inference stage, we predict the task index. We fine-tune a FLAN T5XL model to identify the task and give the input instruction. Task inversion. To enable few-shot learning of new tasks, we propose a method for adapting the model weights without changing the UNet weights. Given a few examples of a new task, we learn a new task embedding. Right? So once you have this embedding space for tasks, you can then take examples of a new type of editing, right? Maybe this type of editing is like changing the alpha channel or something, like some weird type of image editing. And you can then project that into that task embedding space and say, okay, now I'm going to take my original model, which doesn't need any extra crap, and I'm going to condition it on this task vector, and now it's going to be able to do what I want. So it's the magic of task embeddings. A model can be employed by conditioning on the learned task, and it can still handle the original task by relying on the initial task embeddings. Sequential edit thresholding. Applying the model repeatedly in multi-turn editing scenarios aggregates reconstruction and numerical errors. To mitigate this, we add a per pixel thresholding step after each edit turn. We use the pixel value in the output image only if the alteration surpasses a specific threshold. Ooh, okay, so that's, I mean, this isn't great because it's like some hard-coded special bullshit that like they're, you don't want extra complexity like this, but it seems like basically if you don't change the individual value of a pixel too much, right? Like, so if you perform some edit and this yellow pixel here only changes very slightly, they're not going to change it. So they have like some manual threshold here. So generally you don't want to see this, right? These kind of like little tricks like this that just give you one extra random thing that you have to basically decide here. You have to basically decide what this arbitrary threshold is, right? Ideally, less complexity is better, but sometimes you can't help but add some complexity for the sake of performance, right? Like, where did this number come from? 0.03, like what? Evaluate the ability of emu edit to follow user instructions faithfully and preserve the visual fidelity of the original image. Evaluate the performance, conduct a comprehensive ablation study, ablate the contribution of the computer vision task to the model performance. Okay, so similar to the first paper we read, they're going to do a little bit of an ablation and then see which parts are more important. So you have your prompt and prompt, magic brush, instruct pix to pix, null text inversion, and then R's. But these are the fucking Garbo metrics. So this is what I was saying before. Like, these metrics are not good. So this doesn't actually tell me anything. I want the human evaluation. Where is that? Okay, so here's the human evaluation. Text alignment, image faithful. So these are the ones that matter. 81 compared to 98 compared to 74. Okay, so the PNP kind of does the most of the heavy lifting there. Why isn't there nothing here? Doesn't that kind of feel like... See, this is why these numbers can be misleading. Like, look at this. Here, it seems like this one is the best, but here it's very clearly this is the best. So you can only trust the humans, right? Don't trust these quantitative metrics here. To collect a data set, we take different approach. 7 different categories. Background alteration, image changes, global image changes, style altercation, object removal, object addition, and each of these is going to have like a different type of text embedding, right? Or a different kind of task embedding, and then you can interpolate between that, right? So there's going to be a task embedding for object removal and a task embedding for style change, right? And if you want both of those, so you come up with some text description of what you want the edit to be, that text description can be some combination of all of these, right? It can be like an interpolation of those. Localized modifications, color texture alterations. We task crowd workers to devise relevant, creating, and challenging instructions. They probably should have used a vision language model. That would have been cool. To support evaluation, we additionally collect an input caption and output caption. We ask annotators to ensure that the captions capture both important elements and images that should change based on the instructions. Okay, ablations. We train 2 models. Adding the detection and segmentation tasks improves the model performance in region-based editing tasks. We observe that image-to-image translation tasks improve the performance of freeform editing tasks. So there's transfer learning benefits here. Contribution of learned task embeddings. Okay, so without task embeddings, oh my god, but we don't have it with the humans. Without detect segment, without im translation. So this is with and without the extra computer vision tasks, which is detecting and segmenting. And then this is with and without the task embeddings. So higher is better, lower is better. So you can see here that without the task embeddings, you get the lowest clip score here. But this is like barely lower, which is why I don't like these type of metrics, because it's really hard to actually read what's going on here. Or not read, but understand. Acknowledgement. Okay, let's see if there's anything interesting here in the appendices. So, okay, so here we have a little chart that tells us the different tasks, right? So for each of these tasks, you're going to have a different, you're going to learn a different task embedding. And you can kind of see how there's a lot of different types here. You have text editing, style editing, global editing, background removal, texture, changing, adding things, removing things. And here are the computer vision tasks. Instant segmentation, semantic segmentation, pose detection, normal map, depth map. I really like this idea of like basically some kind of task embedding to condition a diffusion model. That just seems so cool. Color. What do we got here? Number of tasks excluded. God, they need to do the human studies for these. Don't give me these numbers. These numbers tell me nothing. Here we go. Boom. Task. Local global add background. Okay, so slightly better. Task-specific experts on image editing tasks. Okay. Was there anything else I wanted to show here? I think not really. I think we pretty much got through most of these, so why don't you guys ask some questions, and then we'll review what we did today, and maybe we'll leave 5 minutes at the end to rant on the future of OpenAI. How about that? Question from Josh Phillips. What is the robot's name? It does not have a name. I don't know what to call it. I've just been calling it humanoid, but I don't know. Maybe you guys pick a name. Maybe we do like a Discord poll or something like that, and you guys get to pick the name. I feel like that would be cool, right? Okay, let's summarize what we did today. So today we reviewed a couple different papers from Meta called Emu Video, Emu Edit, and then we also looked at the original Emu paper. And all of these papers are basically 2D images and video, right? So they're basically generating a two-dimensional image or a video, which is just a sequence of two-dimensional images, using a latent diffusion model. And the latent diffusion model is called Emu, which is basically the name of a large flightless bird, which this is what it looks like, which basically is in line with Meta's llama. You know, like they have this whole naming scheme now, so reserving all the cool animals. Okay, so the original text-to-image latent diffusion model called Emu, there's nothing really that crazy about this. If you've been with us for any of the stable diffusion papers that we read, this is basically the same thing, except it's trained on Meta's dataset and trained entirely by Meta so that they basically have full rights to this. They can do whatever they want with it. They can, they don't need to be dependent on some external group like Stability AI and their model. Like, they're not interested in that. Versus these models here, Runway ML and Pika Labs, these are just startups. They don't have the type of money to train things from scratch, so they're going to be using SDXL as the starting point, versus Meta is using this one, Emu, as the starting point. So now that you have Emu, which is a latent diffusion model, right? It's a diffusion model that works in the latent space, and that latent space is the result of an encoder and the decoder. Then they basically go two different ways. One way that they go is in the video generation space, where they're like, okay, well, we used the text-to-image model, Emu, to create an image, and now can we use that image to create a video, which is a sequence of images? And basically what they do is they create a state-of-the-art, and they evaluate, and they claim state-of-the-art, but then they actually show you in a very clear way that, hey, we got a bunch of people, we sat them down, we showed them a bunch of fake videos, and pretty much everybody agrees that our videos are the best. So I think that's a perfectly good way of saying that you're state-of-the-art. If you're not willing to do this, you shouldn't be claiming state-of-the-art, so I'm totally okay with them claiming that. The way that the model works is basically, there's a couple different models here. This makes it look a little bit more simple than it is. It's a little bit more complicated than this. So they're training, they have a couple different models. They have one model, which they call the F here, script F, and this model will basically take a pre-trained text-to-image diffusion model, and then it'll add these temporal convolutions, right? And then it'll also add a little bit of one extra channel to the spatial layers inside the frozen unit. So they're keeping pretty much everything else the same, right? They leave the text encoder frozen, they leave the encoder frozen, they leave the decoder frozen. The only thing they're really changing is they're adding some extra stuff in here to the unit and then pushing gradients into that. So the extra stuff they add it is quite significant. They're almost like doubling the size of doubling the number of parameters in that UNet from 2.7 billion to plus another 1.7 billion. And then they feed basically the entire video, or they do the entire video at once, right? So they're basically concatenating all the latent images, which are going to have one for each frame of the video, and you're feeding that entire brick of latent images concatenated in the channel dimension into this now latent diffusion model, which now has the temporal convolution, right? And that's the first model. And the first model, which is trained in three basically progressively more and more complicated pre-training steps. So the pre-training for that first model, which is the low frame rate model, is basically trained first at a lower resolution, then at a slightly higher resolution, then at a slightly even higher resolution. And then they have another model, which is initialized from that low frame rate model, which they're calling the interpolation model, which is basically kind of like the super resolution model, except this is like in the temporal. It's like it's increasing the resolution in the temporal dimension. So this second model, which they call script I, is basically just a bigger, badder version of this original model that gives you the rough ones, right? And it just basically fills out the number of frames. So kind of complicated. There's 3 different models here. There's the original text-to-image diffusion model. There's the F, which is the low frame rate one, and then there's the one that takes it to the higher frame rate. And then each of those has a slightly complicated training process where they have this pre-training that is at increasingly higher resolutions, and then they have the fine-tuning, and the fine-tuning data set is automatically chosen based on some quantitative metrics here. So a little bit complicated. And ultimately, I feel like this is still just a intermediate step. You know, at the end of the day, we're talking about like 3-second videos at 16 FPS. You know, like this is not you're not gonna generate like the next Game of Thrones with this type of model, right? Maybe you can generate TikToks with this, but I feel like we still have another 2 to 3 to 4 years before we have, like, to me, what the end state for this, which is going to be, should be something like 60 frames per second and like much longer than 8 seconds, right? Or 4 seconds or whatever this is, right? So we're still kind of in the early stages of video generation. Another important thing that they did here was they used zero terminal signal to noise ratio noise schedule, which is a bug in diffusion models, and there is a video for that. Check that out. And let's summarize the second paper. Okay, so the people at Meta created this EMU text-to-image model, right, which is basically their version of Stable Diffusion, and then one group went, the Ishan's group, went and created EMU video, and then a separate group of different people went and created EMU Edit. And EMU Edit is effectively Meta's version of DALL-E 3. DALL-E 3 is comes from this paper, which is Instruct Pix to Pix. And Instruct Pix to Pix is basically you take a pre-trained diffusion model. Specifically here they use DALL-E. And the robot officially died. So there you go, guys. That's it officially dying. It ran out of battery. But basically they generate prompts for it, and then they generate these pairs, and they fine-tune on that, and then that's Instruct Pix to Pix, and here Meta basically does their version of that, except they do something very cool and very tricky, which is they use task embeddings. So task embeddings, they claim are novel, so they're like, oh, we're going to do this novel task embeddings, but the cool thing, or at least not cool thing, but the interesting thing is that actually I recognize that this comes from an older robotics paper. They might not even be aware of this, but the idea of task embeddings is that you can take any set of tasks, right? Like in this case, the tasks are things like, here, let's go down to the actual tasks. Things like remove a specific thing, add a specific thing, change the texture of a specific thing, change the background, right? Change the style, right? All of those things are different types of edits that you might want, and you're specifying those edits in the form of text. And that text, which is something like remove the tail, add a pink jacket, that can be kind of ambiguous to the model, so that whenever you actually give it, change one of the paws to a robotic paw, it doesn't really know what you mean. So by learning this embedding space for tasks, right, this learned task embedding space, you can then take any task, project it into that, so you can pretty much do any of that. But more importantly than that, you can take user-based instructions and convert them into a task embedding such that that task embedding is a combination of all these different tasks, which makes it much easier for the model to know exactly what you're doing. And then they basically, other than that, it's largely the same. They're basically just conditioning a latent diffusion model on this task embedding. So here, this conditioning, just think of it as like the little task embedding, which is some vector that represents that task that needs to be done, is getting fed into the UNet, and they're using the same exact latent diffusion model that these guys use, which is the EMU one. And that's pretty much it, guys. 2 pretty cool papers. State of the art in video generation. You know, you love to see it. These are really, really cool. I still think we got some space to go, but I think if you give this another year or 2, I think it's going to start getting pretty cool pretty fast. Yeah, and then that's that. Let's maybe talk about OpenAI. So what happens with OpenAI? So I don't know. I don't have any insider information. I don't know Sam Altman. I'm not in his DMs. I'm not in Ilya's DMs. But it seems to me like what's probably going to happen is you're going to have basically a different type of Anthropic, a new Anthropic led by Sam Altman, Greg Brockman, and then there's probably going to be like a contingent of people from OpenAI that leave OpenAI. OpenAI, the brand might disappear, right? So if you're Microsoft, OpenAI, the brand is kind of tainted now, right? You don't necessarily want that brand. It was a lot of association with Altman. So what might happen, it might be what Google did with DeepMind. So Google merged Brain and DeepMind together, right? And I think you might see a similar thing where Microsoft is going to take the OpenAI and it's going to take whatever Microsoft research lab that they have and then they're going to kind of merge them together. So that's another thing I suspect will happen is that Microsoft will kind of start to get rid of that OpenAI brand. But overall, I think it's a win for open source AI, right? It's kind of like, it kind of sucked that the best AI out there was being created by a company that was very secretive and very kind of anti-transparency, So I guess it's good that they're basically hamstringed, right? They got shot in the knee. They took an arrow to the knee, so they're not going to be able to move as fast, which means that all the other people in the race can catch up. So people like Meta, who are much better about being open source, which I think is better. I think open source is a better way to get safety anyways, right? To me, I think it's like kind of like the nutrition label. It's like, I want to know what's actually in these AIs, how they're training them. So to me, going out there and publishing everything, telling people what you trained on, telling people about your data set, telling people all the different hyperparameters, that's the way that you get safety, right? If someone tells you, hey, the way to get safety is for you to let me decide, and I'm not going to tell you why I'm doing things. You just have to trust me. Trust me, and it's very important that you don't know what I'm doing because that's how I'm going to keep you safe. If you know what I'm doing, then I can't keep you safe. So that argument is bullshit, and I'm glad that the people who believe in that argument are less powerful. But I don't know. I don't know what I'm talking about, guys. I don't have any secret power. I'm just some guy in his house with a little robot that is now dead. So I'm sorry, little robot. Sam equals product versus Ilya equals research. Sam wanted to push commercialization. Yeah, but is Ilya open research or secret research? If OpenAI starts publishing papers again, that would be awesome, right? If Ilya's like, hey, let's start publishing our papers, that would be such a huge win. But if Ilya's like, hey, I want to be a research person, but I don't want to publish anything, then that sounds terrible, Do you work at a corporate job? I do not work at a corporate job, but I have worked at corporate jobs before. I've worked at Amazon and Google, so I've been in the big tech giants. I do have some idea, and I've also worked at very small startups and even made my own startup. So I have ideas about startups and tech giants. What else? Very interesting to see if Sam and Greg move towards more open or more closed. Yeah, watch Greg and Sam create basically the Palantir, like some kind of like AI for the military industrial complex. That would be fucking brutal. Lava can pick the name. Ooh, using a VLM to pick the name of the robot. That would be cool. Okay, I think we're out of time here, so I'm going to blow the horn, and then we're going to end it there. Thank you, John, Spyro, Liu, the Yivian, 87GN, Josh, Darshan, Khalil, Christopher. Who else? Joseph. I'm sorry if I missed your name. I'm just trying to like scroll up here. Oma, Ed, everybody, thanks for watching. Tomorrow we'll be doing some other stuff. I think the paper tomorrow is more about 3D, so if you're interested in text to 3D, definitely tune in. But hope you guys have a great weekend, and I'm going to try to blow this horn, but it's very difficult to blow, so apologies if it takes me a couple times.